Thanks for joining me today for this session, which is about thinking serverlessly. My name is James Bezic, and I'm a developer advocate here at the AWS Serverless team. And today, I'll be showing you how to go from business problems to serverless solutions by using a serverless approach. We only have 30 minutes today, and this is a 200-level session, so I'm going to cover a few different areas. First, let's review where we've come from, the world of servers, and how this has influenced our application architecture. From there, I'll talk about how we change this thinking and find a new place to start in designing serverless workloads. I'll cover some good practices to keep in mind when you start building solutions serverlessly. And then for most of this session, I'll spend going through 3 different examples of business problems and how you can approach these serverlessly. At the very end, I'll wrap up with a quick summary. Many of us started as developers by working in a server-based environment. Whether you've used on-premise servers or EC2 instances or an orchestration service like Elastic Beanstalk, it's typical to use servers for certain common tasks. State management is a major role for servers, whether that's for user sessions, caching, or tracking the state of shopping carts, for example. Often, servers act as monolithic containers for functionality. We often build multiple features or functions together into one server. This often leads to one version for one server, and we may handle versioning by installing new versions of applications on different servers. So the server is this atomic unit in our thinking, and it's often tightly coupled with the software that resides on the server itself. But there are some limitations with the old model. It's difficult to scale. Session state, for example, is tied to a single server. Also, scaling is not immediate and often requires some planning for handling peak loads. It can also be very wasteful. Anytime you're not running with 100% capacity, you aren't using all of what you're paying for. And very few servers run continuously at 100%. There's a lot to manage that's not related to your software as well. There's the operating system, networking, and security. It's really an ongoing job just to keep the servers running. For example, to run a production website with a moderate amount of traffic, you would need this kind of configuration. This is from a reference architecture that we published a couple of years ago. WordPress represents a massive amount of server usage on the web, so I chose this example, but it could really apply to any LAMP-style application. Every time there is a web page request here, this web server is querying a relational database for the page structure, loading plugins and themes to create an HTML page, and then serving that rendered page to the visitor. This all seems like a lot of work to serve a static web page. When we talk about serverless, people often assume it's just the EC2 instances that we're replacing, but in production systems there are many interconnecting parts that you have to manage. There's security groups, subnets, auto-scaling policies. You really need a cloud architect or a DevOps professional to help you manage all of this. In serverless, we aim to remove server management and operational overhead. The goal, more than anything else, is to free up your development time to focus on the parts of your applications that your customers see and the parts that differentiate your business. So this is the last time we will see a server for quite a while. When you start to build serverless applications, it may sound obvious, but the server disappears. This means that many of the things we habitually use servers for will change. The good news is it's not difficult, but it's worth talking about some general guidelines first. The approach I'll be showing today is based on some tenets. The first is features first. Breaking down the application to the simple things that it does can help what I call avoid monolithic thinking. You'll see this in the process later. Serverless applications tend to be a federation of functions and services instead of monolithic groups, and these align to functions and features within your application. Next, focus on events. Events are the key to serverless applications. An event can be an HTTP request, a timed interval, or an IoT button press. It's what causes the serverless workflow to happen. The AWS ecosystem is a rich source of events, and this is key to building a well-designed serverless application. Statelessness. This can be one of the harder ideas to adopt if you come from servers. It can be difficult to conceive where the state goes to once the server has gone. In the exercises later, I'll show how we can approach this, because this is really the key to on-demand scaling. Think about the flow of the data in your application early. AWS provides a range of different data solutions, and choosing the right ones for a given problem will inform what other services you need in a serverless design. And always be thinking about the services first. AWS has a broad range of different tools that you can use in designing solutions. If you make your Lambda functions the center of the design, you're probably not leveraging all of the other services effectively. Many people who are new to serverless think that it's synonymous with Lambda. But Lambda is only the functions as a service offering that runs your code on demand, and most of the time, it will be the glue between different services. We rely upon services like API Gateway to provide an interface into your application, or DynamoDB for low latency web-scale NoSQL storage for your apps, or S3 for durable long-term object storage of user data. And for very complex workflows, we can orchestrate these easily with step functions. Events, notifications, and queues, these are all important in managing data across your applications. And then there are specialized services as well, designed for certain use cases. Kinesis for real-time ingestion of streaming data, or IoT for interacting with the Internet of Things, and Elastic Transcoder for processing large media files. Lambda can really connect with almost anything within AWS, which means you have the full access to the power of machine learning, IoT, analytics, media processing, and web, mobile, and digital services. These services are all tools in your serverless developer toolbox. Mix and match them to solve your problems. The key to remember here is that these are all pay-as-you-go services, so whether you use an enterprise-grade database like Aurora Serverless, or a petabyte-scale data stream ingestion system like Kinesis, it makes it very easy to experiment without any long-term commitment. My point here is not to overwhelm you with icons, but to show there are many options available to us as serverless developers, and Lambda is the key to bringing these together in our applications. We'll be using some of these in the solutions today. There are millions of customers using Lambda today. Over time, we've seen serverless architectures emerge that work well, and best practices from customers that have a serverless-first mindset. Part of building a serverless solution is understanding how Lambda fits in. Lambda is ephemeral and runs on demand. It supports many runtimes natively, such as Python, Node.js, Java, and .NET. But you can also bring your own runtimes, such as PHP, Erlang, and even COBOL. A Lambda function runs in response to events. Something has to trigger the code, which could be an HTTP call, for example, or an event from an AWS service like S3 or EventBridge. Because functions have a brief lifespan, you should treat them as being stateless. Lambda also scales automatically so that your Lambda code only needs to handle the business logic of the task and not worry about managing load or traffic. And so, given the attributes of Lambda, there are some best practices. First, avoid lift and shift. Lambda functions are not mini servers, and often lift and shift tries to use them this way. It's better to have one function per purpose than one massive monolithic function doing everything. Functions should usually be very small. It's common to have functions that are only 20 to 50 lines of code that finish within a few hundred milliseconds. Smaller is easier to build, test, and maintain. On choosing runtimes, compiled languages like Java have a higher startup time, but very fast processing. Interpreted languages like Node.js are much faster to start, but may be slower in runtime. So choosing the right runtime can make your apps faster overall. Generally, Lambda functions should contain only the plumbing and business logic between services. We say transform, don't transport data with Lambda functions. Beyond Lambda, there are some good serverless practices too. Infrastructure is disposable. Feel free to spin it up and down as needed by your workload. Asynchronous processing is extremely powerful and scalable. It can be useful for decoupling microservices, but also it's an important mechanism for handling scale in distributed applications. If you use services like SQS, this can help your workload handle virtually limitless amounts of traffic in a durable and reliable way. Each function has one runtime, but serverless apps often have many functions. You can mix and match runtimes in your overall solution. This means you might choose Python for a data-intensive task, or Node.js for JSON handling, or other runtimes depending upon your team's skills. Security is incredibly important. If you apply the principles of least privilege from the outset, you can build highly secure serverless applications. I recommend diving into IAM functionality to see how powerful this can be for securing your apps. Finally, automation can really accelerate your development. While learning in the console is fine, when you're ready to build production applications, frameworks like SAM, or the Serverless framework, can help minimize manual errors and create repeatable, versionable deployments in code. These are really powerful. So now let's turn to the example problems for our business solutions and how we can approach these serverlessly. In each example, I'll provide a problem and an initial solution, and then I'll add some additional requirements to make the problem harder and see how that changes the architecture. In each solution, I'm showing only one way of solving the problem. In real life, there are many other valid approaches too. In the first problem, I need to build a serverless application to support a customer review form submitted from a web page. I assume in this system that there's already a web page with a form and a button, and it just needs to post a review to my serverless backend. And the web page can do this with JavaScript. In the server-based approach to this problem, this might involve adding new functionality to a web server. It could also mean adding a new table to an RDMS database to capture this data. But in the serverless solution, it's actually a lot easier. So first, I'll create a DynamoDB table to hold the results that are submitted by the website user. Next, I need to create a way for the web page to interact with that table. For that, I use API Gateway to create a publicly accessible endpoint where the website can post the data to. Then I need to link the API Gateway endpoint to the DynamoDB table, and for that, I can use a Lambda function. So the function will take the parameters or body from the API call and create a new item in the DynamoDB table with that data. And that's actually it. That's all we would need to use to solve this challenge. In an advanced use case, it's also possible to post the data directly from API Gateway to DynamoDB and skip the Lambda function entirely. This is called an API Gateway service integration. But for now, let's keep the Lambda function in place. So now let's add a new requirement. We collect reviews in English, French, German, Italian, Portuguese, and Spanish, and we need to convert these all to the same language. We have two options. One is to modify the first Lambda function to call AWS Translate and store the result in DynamoDB. Or we can use DynamoDB streams. DynamoDB can invoke a Lambda function when data changes via a stream. Now the benefit of option one is it's simpler, especially if you expect most reviews to not be in English, but it does trend towards the monolithic by having one function doing two things. So if we use option 2 instead, this doesn't affect any existing code. The new function is called for every DynamoDB change, so we have to filter for any new items coming to the table. So overall, this causes more function calls, but actually is a cleaner architecture. So in this solution, a second Lambda function is invoked when the review is added to DynamoDB. This calls Amazon Translate for the translation, and the result is stored back in the DynamoDB table. Now, what happens if we allow users to upload an image along with their text review? So in a server-based architecture, now the server must handle media and temporary space and uploads to somewhere permanent. And so that puts a lot more load on the server, and there are implications to handling this at scale. There are a couple of different options we have here with the existing architecture. The first is to modify that first Lambda function to return an S3 pre-signed URL. Then we could create a second API Gateway route for a new function to route the S3 pre-signed URL. So with this pre-signed URL, the front-end application uploads the binary directly to S3. So in the first case, the URL would return to the front end with this S3 URL. It's simpler because we've just got one function, but it trends towards the monolithic because we have one function doing two things. So in this second idea, we add this second function with the second API Gateway route. Doing this doesn't affect any existing code. Also, there's some parallelization here. Both functions are being called by the front end at the same time. So it causes more function calls overall, but it's a cleaner architecture. So either way, by doing this, now we have large media uploads handled entirely by S3 and not using our web server or a Lambda function. Now, what if we wanted to identify any negative reviews from customers and email someone, maybe a manager, to take action? So if we were using a server-based architecture, what we would have to do is implement a sentiment analysis system, which is fairly complicated, and also would have to make the server also handle email. So we've got a couple of different options here with our serverless architecture. The first is to modify the Lambda function from the DynamoDB stream to use Amazon Comprehend for sentiment analysis. And the second is to create a new function that's also listening to the DynamoDB stream. So in option 1, this function is already calling translate, and so we'd create a second call to comprehend. So there's fewer Lambda functions with this approach, but it trends towards the monolithic because the function would be doing two things. In the second choice, we add this second Lambda function. This doesn't affect any existing code, and we have the benefits of parallelization. Both functions are being called independently. So overall, this causes more function calls from the DynamoDB stream, and there are a maximum of 2 functions allowed per stream. So you might want to use Event Bridge in the middle if over time you have to add more Lambda functions. Or you could use SNS, depending on the use cases for the email. Finally, for this example, let's add authentication. Previously, anyone could add a comment. Now only registered users can submit reviews. To solve this, we need to apply authentication and authorization. In a server-based architecture, we'd have to put the whole thing behind session-based security. And so this server would now be doing quite a lot. You might need horizontal scaling to better keep up with the demand, and maybe introduce an elastic load balancer with sticky sessions. In the serverless realm, it's actually quite a lot easier. We have a couple of good options. One is to use Amazon Cognito, and the second is to use a third-party authentication provider like Auth0. So the benefit of using Cognito is that it integrates really tightly with API Gateway. If you get calls without header tokens, that doesn't incur any charges to your account. Also, any downstream Lambda functions can be called by API Gateway using the correct IAM policies. In the second case, by using Auth0, you could use a custom authorizer with API Gateway that decodes the JSON web token. And so the authorization system can actually be totally independent if needed. So that's the final architecture for this challenge, which now allows us to add reviews with images. We perform a sentiment analysis on comments, lock down the API to authenticated users, and all of this happens scalably, and we didn't need to change any existing code as new requirements arrived. So in the second example, a global retailer wants to implement a virtual queue for customers and use an IoT button to manage a now serving counter at physical locations. There are really 2 applications here. So in the first application, there's an IoT button, a physical button, that when it's pushed, it sends a message to IoT core. That then invokes a Lambda function that increments a counter value on a DynamoDB table. The second application is the customer display. This is a front-end application that polls API Gateway to get a value from the DynamoDB table. So the second Lambda function here would be optional, since API Gateway could use VTL and a service integration to query the table directly. So in this solution, the front-end application polls API Gateway to retrieve the new counter value from DynamoDB. Polling is actually fairly inefficient because often many calls are not resulting in a new value. So our first new requirement is to make this a real-time display showing the current count. So for this we can use IoT Core to publish data directly back to a front-end application via MQTT or a WebSocket. So we've got a couple of different choices here. We could actually modify that first Lambda function to publish to IoT and DynamoDB. So it could do 2 things. But as I've said a few times before, that trends towards the monolithic when you have one function performing 2 tasks. In the second choice, you could add a function to the DynamoDB stream and publish to IoT Core. The web application then listens to a topic and updates the counter in real time. So this results in 2 Lambda function calls every time the IoT button is pressed. So in this model, this removes the polling and eliminates API Gateway from the cost. but this could also use API Gateway WebSockets instead of the IoT Core solution. But either way, this replaces API Gateway polling with a real-time solution. So in our next requirement, we want the front end to speak the number that's on the counter in the language of the local office. So what we can do here is just remove those last couple of services we were using, and instead we're going to use Amazon Polly to create the audio in multiple languages. The delivery of the audio files into the S3 bucket triggers a Lambda function, which then triggers IoT Core for the delivery of the message. And the message from IoT to the front end contains the S3 audio object name and its HTTP path along with the current count. So now the front end loads and plays the audio file from the S3 bucket based upon browser language settings. So in our next requirement, we want to be able to send a daily click history email report. So this is really the equivalent of a cron job. So to do this in serverless, we can use an event bridge rule using scheduled expressions to trigger a Lambda function at a set time of day. So doing this, the rule then causes the Lambda function to be triggered on a schedule, in this case just daily. It would then invoke a Lambda function that will query the DynamoDB table for the counter and then send the email via SNS. You could also use SES if you preferred. Final requirement is to be able to publish this current count into a mobile app, so users can then see what the wait time is from a mobile app. Well, actually, we don't need to make any changes here, because if it's a web app, it's the same mechanism we're using to publish the counter. We could use Amplify to integrate with the front end, or we could use SNS to push messages, or optionally Pinpoint. So basically, this existing design does work with the mobile front end using the same mechanism. But you have to consider the trade-offs between different options using SNS, Pinpoint, or Amplify framework. So in this final architecture, we now have a solution that can receive physical clicks from an IoT button and publish a count in real time to either a display in the store or on the customer's mobile device, and also email a daily tally to a manager. So in the third example, we're going to create a serverless web application to support a national e-commerce business. So if you think about the characteristics of a national e-commerce application, often these are very high volume. They could have very spiky volume with unpredictable traffic patterns. Often users in this case are geographically distributed across large distances, and you need a high-performance front end with very low latency because it's e-commerce. So our first requirement is to ensure fast performance for visitors in multiple regions. So in this solution, let's split the front end from the back end, and I'll discuss the front end first. If you're using a single-page application framework, also known as a SPA, these are frameworks like React or Vue or Angular. These are a great fit with the serverless model. Those frameworks compile down the application to static assets that are HTML, CSS, and JavaScript files. It's actually fairly straightforward to then take those compiled assets, put them into an S3 bucket, and then serve them through CloudFront. CloudFront is a global CDN with 222 points of presence around the world. And so this completely handles the load of having millions of users downloading your app, and also ensures low latency regardless of where the users are located. Now, instead of putting your files directly into S3 and serving through CloudFront, you can also use Amplify Console. You could make it so this would auto-deploy your application via a Git push, so that every time you commit your code to your favorite Git provider, it would then cause a build and then push your application out to all of your users. So this really simplifies the deployment of your web application and creates an automatic CI/CD pipeline for you. So now what if we want to make this so that we allow users to create accounts, including a social login? Well, there's a couple of options here. One is to use Cognito, which integrates with AWS services, or you could use a third-party solution like Auth0. So the benefits of the first option with Cognito are this deep integration across other AWS services. It can also be very cost-effective because in the free tier, it includes 50,000 monthly active users. It supports username and password type logins, or social logins, and various other types of login depending on the application's needs. The benefits of using a third party are that you might already have an existing alternative in place, and we can easily use a JSON Web Token authentication from another provider. So in this case, you can consider using Amplify Framework for the front-end integration, and that can really help automate the UI components required for password resets, login screens, and other UI components that don't necessarily change from application to application. So what now if we wanted to support uploading and serving user videos in this app? Well, in this case, we can have an API gateway call to Lambda request a pre-side URL for an S3 bucket. The front end then puts the file directly into S3 using the URL. That bypasses any sort of server or other service like API gateway or Lambda. So when the object is put into that bucket, that then triggers elemental media convert to process the file. Then when those files are finished processing, it's put into a second S3 bucket. This triggers Lambda to then store the metadata in a DynamoDB table for either this application or other applications to use. So with relatively little code, this final architecture can deliver a global web application supporting high levels of traffic. It can also accept video uploads at scale and reprocess videos on demand for serving to other parts of the application. So from these examples, you can see how some of the best practices I talked about earlier can help guide a serverless architecture that is adaptable to a changing set of requirements. So let's recap quickly. Start with your features first. Break down the application to the simple things it does. Serverless applications are a federation of functions and services, and these align to the functionality and features of the application. Look at events. Events are key to serverless applications, and events cause serverless workflows to happen. Be stateless. This lets Lambda functions operate with no previous knowledge of previous requests, and this is really the key to on-demand scaling. Start by thinking where the data resides. In object stores, NoSQL databases or relational databases, because this can help guide the logic and interactions that help build customer features. And always think about the serverless services first. In the examples, I applied sentiment analysis, user authentication, media processing, and global low-latency application hosting, all by integrating existing services. This helps to minimize custom code, accelerate development, and helps keep the application nimble for future customer requests. Thanks very much for taking the time to join me today. My name is James Bezic, and I'm a developer advocate here in the AWS Serverless team. If you ever have any questions about serverless, feel free to drop me an email or contact me via Twitter. I can't wait to see what you build. Thanks once again.